Imagine standing on Earth, looking up at the night sky, believing the most dangerous thing out there is a black hole, a cosmic vacuum cleaner that devours light itself. But you'd be wrong. The universe harbors something far more violent, something that doesn't need to pull you in to kill you. It announces its existence in a flash, brighter than 1,000,000,000,000 suns, and in that instant, it can sterilize entire sections of a galaxy without ever crossing the threshold of a single solar system. It doesn't discriminate, it doesn't warn, and if one ever aimed at Earth, we wouldn't see it coming until the killing had already begun. This is the story of the most dangerous object in the known universe, and why everything you thought you knew about cosmic threats is about to change. If you love deep space deep dives, you can subscribe. It helps more than you think. The phenomenon has a name that sounds almost mundane for something so catastrophic: gamma-ray burst. 3 words that describe an event so energetically violent that a single one releases more power in 10 seconds than our sun will produce in its entire 10 billion year lifespan. Picture that for a moment. Every sunrise humanity has ever witnessed, every photon that's ever warmed your skin, every ray of light that's driven photosynthesis on this planet for 4 billion years, all of that energy compressed and then multiplied by orders of magnitude, released in the time it takes you to read this sentence. And that's just an average gamma-ray burst. The largest ones dwarf even this comparison. These events occur somewhere in the observable universe roughly once per day. Right now, as you listen to this, a star in a galaxy billions of light years away might be collapsing in on itself, and within moments, it will punch 2 relativistic jets through its poles and announce its death to the cosmos with a beam of gamma radiation so concentrated, so perfectly collimated, that if you were unfortunate enough to be standing in its path 3,000 light years away, you wouldn't survive. Your planet wouldn't survive. The very chemistry that makes biology possible would be torn apart in the upper atmosphere, and everything beneath would be bathed in radiation levels that turn protective ozone into toxic compounds and evolutionary progress into extinction. But let's start at the beginning, because understanding why gamma-ray bursts are the universe's ultimate weapon requires understanding what they actually are. And the story begins with death, specifically the death of stars so massive they make our sun look like a flickering candle. When a star is born with a mass greater than about 25 times that of our sun, its fate is essentially sealed. It will live fast and die explosively. These stars burn through their nuclear fuel at prodigious rates, fusing hydrogen into helium, helium into carbon, carbon into oxygen, building heavier and heavier elements in their cores through a process that releases tremendous energy. This energy creates an outward pressure that counterbalances the inward crush of gravity. It's a cosmic standoff that can last millions of years for the most massive stars, but eventually, inevitably, the fuel runs out. When the core of such a star exhausts its ability to fuse elements, when it's built up a core of iron that can't be fused any further without consuming energy instead of releasing it, the standoff ends in an instant. Gravity wins. The core collapses. In less than a second, a region the size of Earth compresses down into a sphere perhaps 20 kilometers across. The implosion is so rapid, so violent, that the outer layers of the star have no time to follow. They're still hanging there in space, held up by nothing, when the core rebounds or forms a black hole and the shockwave tears outward. This is a supernova, and it's one of the most energetic events in the universe. But a supernova is not a gamma-ray burst. A supernova explodes in all directions, radiating its energy across the entire sphere of space around it. It's spectacular, bright enough to outshine its host galaxy, but its energy is diluted, spread thin across every possible direction. A gamma-ray burst is something else entirely. It's what happens when that collapse doesn't stop, when the core forms a black hole so rapidly, spinning so fast, that it creates an accretion disk of infalling matter that doesn't fall straight in. This disk, superheated to billions of degrees, becomes a cosmic engine. Magnetic fields twist and amplify. Matter spirals inward at a significant fraction of light speed. And then, Threaded through the poles of this newborn black hole, something extraordinary happened. Two jets erupt, not an explosion in all directions, not a spherical wave, two narrow beams, one from each pole, perhaps only a few degrees wide. And these beams are different from anything else in astrophysics. They're relativistic, meaning the matter and radiation inside them are moving at speeds so close to the speed of light that Einstein's special relativity transforms everything about how they behave. We measure this with something called the Lorentz factor, and for gamma-ray bursts, this number can exceed 300. To understand what that means, imagine you're watching this jet from a safe distance. Time inside the jet is moving 300 times slower than your time. Lengths are contracted, energies are amplified. A photon emitted from inside this jet gets blue shifted so dramatically that even if it started as visible light, by the time it reaches you, it's a gamma ray, the most energetic form of electromagnetic radiation in the universe. These jets punch through the collapsing star like cosmic blowtorches. They bore through thousands of kilometers of stellar material in seconds, and when they break free into space, they don't slow down. They keep going, and as they propagate outward, they create a fireball, a relativistic shock front that sweeps up material and accelerates it even further. Inside this fireball, particles collide at such extreme energies that they produce cascades of secondary radiation, gamma rays, that beam outward in the same narrow cone. This is the burst itself. The initial flash, it can last anywhere from a fraction of a second to several minutes, depending on the type of collapse and the properties of the progenitor star. There are two main categories of gamma-ray bursts, and they tell us about two different kinds of cosmic catastrophe. The long-duration bursts, which last more than 2 seconds, are the ones I've been describing. They're born from the deaths of massive, rapidly rotating stars called Wolf-Rayet stars. These are stars that have already shed their outer hydrogen envelopes through intense stellar winds, leaving behind cores of helium, carbon, and heavier elements. When these cores collapse, the lack of a bulky outer envelope means the jets can escape more easily, and the rapid rotation ensures the jets are tightly focused and highly energetic. The entire event, from core collapse to jet breakout, is called a collapsar. It's a hypernova channeled into a beam. The short-duration bursts, lasting less than 2 seconds, are even more exotic. They don't come from collapsing stars at all. They come from collisions, specifically the merger of two neutron stars, or sometimes a neutron star and a black hole. These are the remnants of stars that already exploded once as supernovae. Neutron stars are objects so dense that a sugar cube-sized chunk of their matter would weigh as much as all of humanity combined. When two of these monsters spiral into each other, locked in a gravitational dance that's been tightening for billions of years, the final moments are almost unimaginably violent. They merge in less than a second. The collision releases a flood of neutrons, creating heavy elements like gold and platinum through rapid neutron capture, but it also creates a black hole, often surrounded by a torus of ultra-dense matter. And once again, if the conditions are right, jets erupt from the poles. Both types of gamma-ray bursts share this fundamental characteristic. They concentrate energy into beams, and this is why they're so much more dangerous than black holes, or even than supernova. A black hole will kill you if you get close. Yes, the tidal forces will stretch you into spaghetti, the event horizon will swallow you forever, but you have to go to the black hole. It doesn't reach out across thousands of light years and find you. A supernova will irradiate nearby planets. Certainly, if you're within 10 light years of a supernova, you're in trouble. But gamma-ray bursts? The danger zone is measured in thousands of light years, perhaps as much as 10,000 light years for the most powerful bursts aimed directly at you. That's a significant fraction of the diameter of our galaxy. The physics of why this is so deadly lies in what gamma rays do to atmospheres. When a burst of gamma radiation hits a planet with an atmosphere like Earth's, it doesn't just heat things up. It triggers a cascade of chemical reactions that destroy the very molecules that protect life from space. Ozone, that thin layer of O3 molecules in our stratosphere that absorbs ultraviolet radiation from the sun, is particularly vulnerable. Gamma rays slam into nitrogen and oxygen molecules in the upper atmosphere, breaking them apart and creating nitrogen oxides. These nitrogen oxides are catalysts. They destroy ozone. One nitrogen oxide molecule can destroy thousands of ozone molecules before it's removed from the atmosphere. Within hours of a gamma ray burst striking Earth's atmosphere, the ozone layer would be depleted by 50% or more. Within days, it could be gone entirely in some regions. And without that shield, the sun's ultraviolet radiation, which is always streaming toward us, would reach the surface at levels biology never evolved to handle. UVB and UVC radiation cause direct DNA damage. They break chemical bonds. They sterilize. On land, plants would begin to die from radiation damage. In the oceans, phytoplankton, the foundation of the marine food web, and the source of much of Earth's oxygen, would be devastated. The ozone layer would eventually recover, but it would take years, perhaps decades in the worst case. And in that time, ecosystems would collapse, food webs would unravel. Mass extinction would not be a possibility, it would be a certainty. But there's more. The gamma rays themselves, during that initial burst, create secondary particles in the atmosphere. When a gamma ray photon hits an air molecule, it can produce electron-positron pairs. These particles then collide with other molecules, creating more secondary radiation. The entire atmosphere becomes a shower of high-energy particles, a cascade that reaches all the way to the ground. Anything on the surface would be exposed to radiation doses far exceeding lethal levels. Not instantly, perhaps, but over the hours of the burst's duration. And remember, this is all happening in the narrow beam of the jet. If you're not in the beam, if you're on the side of the planet, or outside the cone entirely, you might not even know it's happening until the afterglow appears days later. But if you're in the beam, there's no escape, no warning, no defense. The energy scales involved are difficult to comprehend. A typical long gamma ray burst releases about 10 to the 51 ergs of energy in gamma rays alone. To put that in perspective, that's roughly equal to the total energy output of our sun over its entire main sequence lifetime. 10 billion years of sunshine released in 10 seconds. But that's not even the full story. The gamma rays we detect are only a small fraction of the total energy released by the event. The jets themselves carry far more energy in kinetic form, in the motion of the particles streaming outward at relativistic speeds. The total energy budget of a gamma ray burst can reach 10 to the 54 ergs. That's 1,000 times more energy than a typical supernova. It's more energy than a quasar emits in a year. For a brief moment, a gamma ray burst can outshine every other object in the observable universe combined. To make this feel more tangible, imagine if we could somehow convert the energy of a gamma ray burst into something we could see. If you took all the light from every star in the Milky Way, all 100 billion stars, and compressed their combined output into 10 seconds, you still wouldn't match the brightness of a gamma ray burst. And because the energy is beamed, if you happen to be looking down the barrel of that jet, the burst would appear even brighter. The beaming amplifies the apparent brightness by the square of the Lorentz factor. So, with a Lorentz factor of 300, the brightness is multiplied by 90,000. This is why we can detect gamma ray bursts from the edge of the observable universe, from galaxies so distant their light has been traveling for over 13 billion years. We've seen bursts from when the universe was less than 1 billion years old, from epochs when the first galaxies were just forming. One of the most powerful gamma ray bursts ever observed occurred on October 9th, 2022. It was designated GRB 221009A, but astronomers quickly gave it another name: the Boat, the brightest of all time. This burst was so energetic, so close in cosmic terms, that it temporarily blinded satellites designed to detect gamma rays. It saturated detectors. It created a pulse of ionization in Earth's upper atmosphere that disturbed radio communications, and it was 3 billion light-years away. 3 billion light-years, and it still affected our planet. Not dangerously, not in any way that threatened life, but measurably, detectably. It released approximately 10 to the 55 ergs of energy, making it one of the most energetic events ever observed. And it wasn't even aimed at us. We caught the edge of the beam, the peripheral spray of a jet that was pointed slightly away from our line of sight. If it had been aimed directly at us, the effects would have been far more pronounced. Other notable bursts include GRB 130427A, another extremely energetic burst detected in April 2013, and GRB 080916C, which for years held the record for the highest measured energy output. These events are not just anomalies. They represent the upper end of a distribution, the most powerful manifestations of a phenomenon that occurs daily somewhere in the universe, and each one is a reminder that the cosmos is not a gentle place. It's a battleground of extreme physics, where the rules we experience in our everyday lives are bent and broken by energies and speeds and densities that defy intuition. But here's the terrifying question. Has this ever happened to Earth? Have we ever been in the crosshairs of a gamma ray burst? The geological record is frustratingly ambiguous, but there are hints, tantalizing, disturbing hints. About 445 million years ago, during the Ordovician period, Earth experienced a mass extinction event. It wasn't as famous as the asteroid impact that killed the dinosaurs, but it was significant. Roughly 85% of marine species went extinct. The extinction happened in two pulses, separated by less than 1 million years, and it coincided with evidence of atmospheric changes. Specifically, there's evidence of a sudden increase in ultraviolet radiation reaching the surface, inferred from the presence of certain spores and chemical markers that suggest plants and marine organisms were under UV stress. Some scientists have proposed that a gamma ray burst could have been the trigger. A burst occurring within 10,000 light-years of Earth, aimed directly at us, would have depleted the ozone layer exactly as the evidence suggests. It would have caused precisely the kind of extinction pattern we observe, with marine organisms and surface-dwelling creatures suffering disproportionately. There's no smoking gun, no definitive proof, but the hypothesis fits the data uncomfortably well, and it raises a chilling possibility. If it happened once, it could happen again. So how likely is that? What are the odds that a gamma ray burst will target Earth in our lifetime, or in the lifetime of our species? The answer requires understanding both how common these events are and how the geometry of beaming affects the odds. Gamma ray bursts occur roughly once per day in the observable universe, but the observable universe is incomprehensibly large. It contains somewhere around 2 trillion galaxies, so the rate per galaxy is much, much lower. In the Milky Way, we expect a long-duration gamma ray burst roughly once every few million years. Short bursts are even rarer, perhaps once every few 100,000 years in our galaxy, though the rate is highly uncertain. But remember, the jets are narrow, typically only a few degrees wide. If you imagine the full sphere of directions a jet could point, and then calculate what fraction of that sphere corresponds to a beam a few degrees wide, you find that only about 1 in 100 bursts, or perhaps 1 in 1,000, would actually be aimed in any given direction. So even if a gamma ray burst occurs in our galaxy, the chance that it's pointed at Earth is very small. Combining these factors, the probability of a dangerous gamma ray burst hitting Earth is estimated to be roughly once every few 100 million years. Maybe longer, maybe shorter. The uncertainties are large. This might sound comforting. A few 100 million years is a long time, longer than humans have existed, longer than mammals have existed, but it's not infinite. Over geological timescales, over the billion-year history of complex life on Earth, the odds start to add up, and as we've seen, there's at least circumstantial evidence that it may have already happened. The Ordovician extinction is not the only candidate. Some researchers have suggested that other extinction events, or periods of reduced biodiversity, might also correlate with gamma-ray burst strikes. The evidence is weak, contested, but it's there. A reminder that we live in a shooting gallery, and the bullets are made of light. Now imagine what it would actually be like if a gamma-ray burst struck Earth today. Not from billions of light years away, safely diluted by distance, but from a star within our own galaxy, say 5,000 light-years distant, the progenitor star would have to be massive, rotating rapidly, and oriented just right. Perhaps it's a Wolf-Rayet star that astronomers have been monitoring, knowing it's near the end of its life but not knowing exactly when it will explode. And then one day, it does. The star collapses, the jets form. They punch through the stellar envelope and break into space, accelerating to 99.99% of the speed of light. The gamma rays, moving just ahead of the bulk flow, race outward in a cone. 5,000 light-years is a long way, but at the speed of light, the journey takes 5,000 years from the star's perspective. From our perspective, though, we don't see anything coming. The gamma rays and the light from the explosion travel at the same speed. There's no advance warning, no way to detect the threat before it arrives. 5,000 years after the star explodes, give or take, the gamma rays reach Earth. They arrive during a normal day. Maybe it's morning in North America. The sky is clear. People are going about their lives. And then, without any preamble, the atmosphere begins to glow. Not visibly, not at first. The gamma rays are too high in energy for our eyes to detect directly, but instruments would see it immediately. Satellites monitoring space weather would register a sudden spike in gamma ray flux, orders of magnitude beyond anything they've ever recorded. Within minutes, the cascade begins. The upper atmosphere starts to heat. Nitrogen oxides form. Ozone molecules start breaking apart. At ground level, people would notice something strange happening. The sun might seem slightly different. Colors might shift as the atmospheric chemistry changes, but the real effects wouldn't be visible for hours, maybe days. As the ozone layer thins, UV levels would climb. Sunburns would happen faster. Plants would begin showing signs of stress. Nocturnal animals might become more active during the day, sensing that something is wrong with the light. Within a week, the consequences would be undeniable. UV levels would be high enough to cause severe sunburns in minutes. Ecosystems would start to collapse. Phytoplankton blooms in the oceans would fail. Coral reefs, already stressed by warming waters, would bleach and die en masse. On land, crops would wither. Forests would show widespread leaf damage. The food chain would begin to break down from the bottom up, and the ozone depletion would continue because the nitrogen oxides don't disappear quickly. They persist in the stratosphere, catalyzing more and more ozone destruction. Within months, the Earth would be a different planet. The sky would look different, a deeper blue in some wavelengths, hazier in others. The extinction event would be well underway. Humans, being resourceful, might survive in the short term. We could stay indoors during the day. We could use artificial lighting for crops. We could, in theory, rebuild civilization underground or in heavily shielded environments. But the vast majority of species wouldn't have that option. The biosphere would collapse, and even if humans survived the initial crisis, the long-term recovery would take centuries, millennia. The Earth's ecosystems would be fundamentally altered. Evolution would have to start over in many lineages. It would be a reset button pressed by the cosmos, indifferent to the complexity and beauty it erased. And the worst part? We wouldn't know it was coming. Unlike an asteroid, which we can track and potentially deflect, a gamma ray burst gives no warning. The light and the radiation travel together. By the time you know it's happening, it's already too late. There's no time to evacuate, no time to prepare, no time to say goodbye. You just happen to be in the wrong place at the wrong time on a cosmic scale. But let's zoom out. Let's place gamma ray bursts in the broader context of cosmic dangers, because as terrifying as they are, they're not the only exotic threats the universe has in store. There are quasars, the supermassive black holes at the centers of galaxies that accrete matter and shoot jets of their own, jets that can extend for millions of light years. But quasars are persistent. They're not sudden bursts, and their jets, while energetic, are not as focused or as intense as gamma ray burst jets. They're dangerous if you're close, certainly, but they don't have the same sterilization radius. There are magnetars, neutron stars with magnetic fields 1 trillion times stronger than Earth's. When a magnetar undergoes a starquake, when its crust fractures and releases magnetic energy, it can produce a burst of gamma rays and X-rays. These are called soft gamma repeaters, or giant flares, and they can be extraordinarily bright. In December 2004, a magnetar called SGR 180620, located about 50,000 light-years away, produced a flare so intense that it measurably affected Earth's ionosphere. If that flare had occurred within a few thousand light-years, it might have been catastrophic, but magnetar flares are rarer and less energetic than true gamma-ray bursts, and they don't have the same relativistic beaming. There are tidal disruption events, where a star wanders too close to a supermassive black hole and is torn apart by tidal forces. The debris forms an accretion disk, and sometimes jets are produced. But again, these are less energetic and less frequent than gamma-ray bursts. And then there are more speculative threats. Vacuum decay, where a quantum field that pervades the universe transitions to a lower energy state, releasing energy and rewriting the laws of physics as a bubble expands at the speed of light. If vacuum decay ever happens, it would be the ultimate cosmic threat, because there's no defense and no warning. But it's purely hypothetical. We don't even know if it's possible, let alone likely. Gamma-ray bursts, by contrast, are real. We observe them. We study them. We know they happen, and we know they're capable of affecting planets thousands of light-years away. In the hierarchy of cosmic dangers, they sit at the top of the list of things that could plausibly, realistically, end complex life on Earth without any chance of prevention. We detect gamma-ray bursts using a fleet of satellites designed to monitor the sky for sudden flashes of high-energy radiation. The SWIFT satellite, launched in 2004, can detect a burst and autonomously slew its telescopes to observe the afterglow within seconds. The Fermi Gamma-Ray Space Telescope, launched in 2008, monitors the entire sky continuously, detecting bursts at a rate of roughly 1 every 2 days. When a burst is detected, ground-based telescopes around the world swing into action, observing the afterglow in visible light, infrared, and radio wavelength. This afterglow is crucial. It's the light produced as the relativistic jet slows down and interacts with the surrounding medium. By studying the spectrum of the afterglow, astronomers can determine the redshift of the burst, which tells us how far away it is and how long ago it occurred. Some bursts are so distant that their light has been traveling for over 13 billion years, meaning we're seeing them as they were when the universe was a mere infant. The spectra also tell us about the composition of the jet and the environment it's moving through. We can measure the density of the surrounding gas, the magnetic field strength, the energy distribution of the particles in the jet. We can even detect the presence of heavy elements, the ash of nuclear fusion created in the moments before the star collapsed. Every burst is a cosmic laboratory, a natural experiment in extreme physics that we could never replicate on Earth. The most distant gamma-ray bursts, those from the early universe, are particularly valuable. They serve as beacons, illuminating the conditions in galaxies when the universe was young. They tell us about the first generations of stars, the so-called population theory stars, which were made of pure hydrogen and helium, and nothing else. These stars were likely far more massive than any star that exists today, and their deaths would have produced the first heavy elements, seeding the universe with the raw materials for planets and life. Some of these deaths were probably gamma-ray bursts. In fact, gamma-ray bursts may have played a crucial role in shaping the early universe. Think about it. In the first billion years after the Big Bang, galaxies were smaller, denser, more tightly packed. Stars were forming at prodigious rates, and when the most massive of those stars died as gamma-ray bursts, their jets would have carved out vast regions of ionized, sterilized gas. Any planets in those regions would have been rendered lifeless before life even had a chance to begin. Gamma-ray bursts may have suppressed the emergence of life in the early universe, creating dead zones around star-forming regions. Only later, as galaxies expanded and the universe aged, did the threat diminish enough for life to take hold. In a very real sense, gamma-ray bursts shaped the habitability of the cosmos. They're not just a danger, they're a filter, a selection mechanism that determines where and when life can exist. This raises a fascinating question. What would an alien civilization experience if they were close enough to a gamma-ray burst to study it, but far enough away to survive. Imagine you're an astronomer on a planet orbiting a star in a galaxy where a massive star, 2,000 light years away, is about to collapse. You've been watching this star for years. You know it's unstable. You know it could go at any moment. And then, one night, it does. The first sign would be a flash of gamma rays and X-rays arriving all at once with no warning. Your instruments would scream. Your satellites would detect a spike in radiation so intense it would be off the scale. If you were looking at the star through a telescope, you might see it brighten dramatically in visible light as well, though the gamma rays would arrive first and be far brighter in energy terms. Over the next few hours, the afterglow would develop. The jet, having broken free of the star, would begin to interact with the surrounding gas. Shock waves would propagate outward, heating the gas to billions of degrees. The light would shift and evolve, first dominated by X-rays, then ultraviolet, then visible light, then infrared, then radio. Over days and weeks, you'd watch this cosmic firework display, this death rattle of a star, play out across the electromagnetic spectrum. And you'd measure the energy, the spectrum, the evolution of the light curve. You'd calculate the Lorentz factor of the jet. You'd estimate the mass of the progenitor star. You'd search for a supernova component, the slower moving explosion that follows the jet breakout. And you'd realize, with a mix of awe and horror, that you're witnessing one of the most powerful events the universe can produce. A star dying in a blaze of relativistic glory. A cosmic catastrophe that, had it been aimed at you, would have ended your civilization. And maybe, just maybe, you'd look up at your own star and wonder, is our sun safe? Will we ever have to face this? And the answer, for most civilizations, would be the same as it is for us. Probably not. The odds are low, but they're not zero. This brings us to the philosophical weight of gamma ray bursts. They represent a class of threat that's entirely beyond our control. We can't predict them with certainty. We can't deflect them. We can't shield an entire planet from them. They're a reminder that for all our technological progress, we're still vulnerable, still subject to the whims of a universe that operates on scales and with energies we can barely comprehend. Black holes get all the attention in popular culture. They're the monsters, the cosmic predators that lurk in the dark. But black holes are local threats. You have to go to them. Gamma ray bursts come to you. They reach across the void, across thousands of light years of empty space, and deliver death at the speed of light. And yet, there's something beautiful in that, something humbling. Gamma ray bursts remind us that we're part of a universe that's far larger, far more violent, and far more magnificent than our everyday experience suggests. They remind us that the stars are not eternal, that everything in the cosmos is temporary, including us. They remind us that life is fragile, that the conditions that allow it to exist are narrow and contingent. A few thousand light years in the wrong direction, a few degrees of misalignment, and we wouldn't be here. Earth might be a barren rock, its atmosphere stripped, its oceans dead, its evolutionary experiments erased, but we are here, we exist, and we've reached a point in our development where we can look out at the universe and understand, at least partially, the forces that threaten us. We can detect gamma ray bursts, we can study them, we can calculate the odds. We can't stop them, but we can know them, and there's power in that knowledge. There's dignity in facing the abyss and refusing to look away. The universe is not designed for life. It's not hostile to life either. It's indifferent. Stars collapse, jets erupt, galaxies collide, and through it all, the fundamental laws of physics play out without concern for the consequences. Life arises in the quiet moments, in the gaps between catastrophe, in the regions of space where the radiation levels are low enough and the chemistry is rich enough and the time is long enough for complexity to emerge. We're the beneficiaries of a cosmic lottery, the recipients of a series of lucky breaks that stretch back billions of years. And gamma ray bursts are a reminder of how easily that luck could run out. But they're also a reminder of resilience. Earth has endured impacts, volcanic eruptions, ice ages, and possibly even gamma ray bursts. Life has survived, It's been knocked back, certainly. It's been forced to restart, to evolve new strategies, to fill the empty niches left by extinction. But it has survived, and it's likely that as long as the sun shines, and the oceans flow, and the atmosphere holds, life will continue to find a way. Even if a gamma-ray burst were to strike Earth tomorrow, it wouldn't sterilize the planet completely. Deep-sea organisms, bacteria living kilometers underground, extremophils in every sense of the word, would endure, and given enough time, life would re-emerge. Evolution would resume. The experiment would continue. So, when you look up at the night sky, remember this: every point of light you see is a potential source of both creation and destruction. Stars forge the elements that make planets. They warm worlds and drive the chemistry of life. But stars also die, and when they do, they can take entire regions of the galaxy with them. The universe is a forge, yes, but it's also a weapon, and we live in the crossfire. Gamma-ray bursts are the ultimate expression of this duality. They're the brightest, most energetic events in the universe, visible across cosmic distances, a testament to the power of gravity and nuclear physics and relativistic mechanics. But they're also death on an unimaginable scale. They're the price the universe pays for having stars massive enough to create heavy elements, for having the dynamical processes that forge black holes and neutron stars and magnetars. Without gamma-ray bursts, the universe would be different. Perhaps less vibrant, perhaps less dangerous, but certainly less grand. And in the end, isn't that the lesson? That grandeur and danger are inseparable, that the same forces that create beauty and complexity also create destruction, that the universe is not a safe place, and it never was, and it never will be. But it's a place of wonder, a place where stars explode and jets erupt and galaxies collide, and somewhere in the midst of all that chaos, on a small blue planet orbiting an unremarkable star, life looks up and tries to understand. Gamma-ray bursts will keep happening, stars will keep collapsing, neutron stars will keep merging, and the beams will keep lancing out across the cosmos, invisible fingers of radiation that touch everything in their path. Most of the time, they'll pass through empty space. Most of the time, there will be nothing there to kill. But occasionally, once in a few 100 million years, one of those beams will intersect a world where life has taken hold, and in that moment, the universe will remind that life of its place, not at the center, not protected, but surviving, for now, in the gaps between the light